dithermic wall, a conducting wall that allows heat to flow from one to another. In this case, thermal equilibrium is attained in due course. In general, whether or not a system is in a state of equilibrium depends on the surroundings and the nature of the wall that separates the system from the surroundings. Consider two gases A and B occupying two different containers. We know experimentally that pressure and volume of a given mass of a gas can be chosen to be its two independent variables. Let the pressure and volume of the gases be PA and VA and PB and VB respectively. Suppose first that the two systems are put in proximity but are separated by an adiabatic wall. An inserting wall can be movable that does not allow flow of energy from one to another. The system are insulated from the rest of surroundings also by similar adiabatic walls. The situation is systematically. In this case, it is found that any possible pair of values PA, VA will be in the equilibrium with any possible pair of values PB, VB. Next, suppose that the adiabatic wall is replaced by a dithermic wall, a conducting wall that allows energy flow from one to another. It is then found that the microscopic variables of the system A and B change spontaneously until both the systems attain equilibrium states. After that, there is no change in their states. The pressure and volume variables of two gases changes to PB hash, VB hash and PA hash and VA hash, such that the new states of A and B are in equilibrium with each other. There is no more energy flow from one to another. We then say that the system A is in thermal equilibrium with the system B. What characteristics the situation of thermal equilibrium between two systems? You can guess the answer from your experience. In thermal equilibrium, the temperature of the two systems are equal. We shall see how does one arrive at the concept of temperature in thermodynamics. The zeroth law of thermodynamics provides the clue. Zeroth law of thermodynamics. Imagine two systems A and B separated by an adiabatic wall while each is in contact with a third system C via a conducting wall. The state of the system will change until both A and B come to thermal equilibrium with C. After this is achieved, suppose that the adiabatic wall between A and B is replaced by a conducting wall and C is insulated from A and B by an adiabatic wall. It is found that the states of A and B change no further, that is, they are found to be in thermal equilibrium with each other. This observation forms the basis of the zeroth law of thermodynamics, which states that two systems in thermal equilibrium with a third system separately are in thermal equilibrium with each other. Thank you.